All right. Hello, everybody. I am sitting outside. I thought you maybe would like a little screencast on how to do this worksheet. Feel free to fast forward the worksheet. Fast forward the screencast anytime so that you can get to the question that you have. But I'll go through the entire worksheet. But I do just have to hesitate a second because I'm sitting outside and I enjoy nature. And right in my backyard, you probably can't see it actually. I'm trying to make it so you can see it, but there's two little ducks just sitting in my backyard. I don't have a pond or anything nearby, but there's a mama duck, a mallard, and a male and a female mallard duck. And that cracks me up. That quacks me up. All right, sorry. I'm going to go ahead and push my Chromebook down. You're going to be looking at the sky. Maybe a great blue heron will fly by because one just did a moment ago. You might hear birds chirping, dogs barking, children playing, or cars driving by. Hopefully not any garbage trucks because they're so loud. But anyway, fast forward me and get to the ones that you need help with. So question number 1 is just a review of specific heat that we did yesterday. The equation I had already written down, Q equals mc delta T, and in this case, Q, remember, is heat. We're going to use delta H to mean enthalpy. So Q is heat, and we're going to measure that heat in joules for this particular problem. So for this problem, we're going to say Q is what we're looking for, so M is the mass, and in this case, that was 10.0 grams of aluminum. The specific heat of the aluminum was 0.90 joules per gram times degrees Celsius. And then the temperature change, it looks like it was a 33 degrees Celsius temperature change. Interestingly, you can keep these in Celsius. You don't have to convert them to Kelvin the way you did with the gas law problems. However, you could convert them to Kelvin and it would still work. So let's go ahead and multiply it out. 10 times 0.9 times 33 gives us an answer of Q is 297 joules, and then it suggests converting it to calories just for the practice. So to do that, 297 joules, our conversion factor, we would want to put what we're trying to get rid of on the bottom, which is 1 joule. Actually, I'm going to do that differently. It's 1 calorie for 4.1. Why did I make a scribble when I'm using this thing? There's no need to scribble, right? 4.184 joules to every 1 calorie. There we go. And if we put that into the calculator, 297 times 1 divided by 4.184, and we should get 70.9, which it's actually 70.98. So that rounds out with sig figures to 71.0, and that would be, in this case, we're doing small c calories. All right, moving on to our delta H problems. So question number 2 says, what are the delta H values for the following reactions? Are they endothermic or exothermic? The first thing we need to do is to write out the equations. Remember that you have to balance your charges and everything. So sulfur and oxygen converts to sulfur dioxide when you do that. Remember, oxygen is always diatomic. And then that forms sulfur trioxide, which is SO3. Oh, I should try switching up colors here when I go to balance. So then to balance the equation, we're going to put the right coefficients in front, and that now is our balanced equation. So now we're going to take a look at, the table on the other page. Oxygen is an element, so oxygen is always going to have a delta H of formation value of 0, so we don't have to worry about that one. But to figure out the delta H for the entire equation, remember that delta H is telling us how much the energy is changing. And if it's a positive, then it's a positive value, then it's an endothermic reaction. And if it's a negative value, it's an exothermic reaction. So now I am going to, get rid of that. I'm going to try to pull up our table. There we go. And the first thing that we're going to look for is, actually, I'm going to go to the products first, because remember we do products minus the reactants. So I'm going to go ahead and go to the product, and the product is SO3. So I'm going to scroll down here until we find sulfur trioxide, and still looking. And I cannot read it in the dark here, so I better... I'm stuck on something, so give me just a moment. What did I misunderstand here? I should have sulfur oh, that is sulfur trioxide. Gosh, my eyes are so bad, you guys. I'm so sorry. So sulfur trioxide is right there, and it's got a minus 454.51. And in our equation, if we go back to our equation, let's see, I'm going to switch colors one more time. Let's go with this blue. So I'm going to say there are 2 of them. So I'm going to multiply it by 2. 2 of this one. We're doing the sulfur trioxide first. And that has the delta H of formation is 454.51. And that is in kilojoules per mole. And then from that, we're going to subtract the reactants. There are 2 reactants. I'm going to put them in brackets just so you know what I'm putting in reactants. So the first one is the sulfur dioxide. And so I go back to my sheet and I look up sulfur dioxide. And in this case, sulfur dioxide is a minus 296.83. So I'll go back to my thing, and we have 2 of them. So I'm going to do 2 times the minus 296.83 plus, and then this one is going to be 0. Because the oxygen is a 0. So I'm going to close that off in brackets. So now I'm going to figure out the math on this one. And when I plug it into my calculator, 2 times 454.51, which is a negative, is minus 909.02. And then from that, I'm going to subtract 2 times oops, I didn't do that right. 2 times 296.83, which is also a negative. Close the parentheses. And I should get for a final answer equals minus 315.26 kilojoules per mole in that circumstance. All right, let me know if you have any questions about that one. Let's move on to the next one. We will try letter B. This one has already been written out for us. Now we just need to balance it. So to balance it, I see that we're going to need to throw, I know what the balanced equation is already, so I'm not going to waste time doing it in front of you. So I'm just going to throw in the balancing for you. 3, 2, and 2 gets it all balanced. And now we're going to go ahead and look the things up that we need to. So I'm going to start on this side again. Maybe I'll switch colors to make sure you're clear on that. I'm going to start on the products side because you always write them first, and then I'm going to subtract the reactants from it. So on the product side, as I look it up on the table, I'm going to look for, in this case, I'm going to look for the sulfur dioxide, which we did in the last problem, actually. So we can just copy that number down again. And this time I'm going to look for liquid water, and liquid water, H2O. We have to make sure it's the liquid version. Oh, my eyes are so bad. This is really hard for me to do. Bring it up. Oh, that's because I didn't go far enough up. There we go. The liquid oxygen in this case, minus 285.83. Now I'm going to go back to the worksheet and I'm going to get all of that balanced out. So it says we have 2 of the the liquid water. So I'm going to go ahead and put that in brackets. So in brackets, I'm going to do 2 times, and then the liquid water is a minus 285.83 kilojoules per mole. And then I'm going to add that to 2 times the sulfur dioxide. There's the sulfur dioxide. 2 times, and the sulfur dioxide we already knew from the previous problem was a minus 296.83. 6.83. And that's my close bracket. So now I am done with the products. From that, I'm going to subtract the reactants. There are 2 H2S's. So if I go back to my table and I look up H2S, I see it right there near the bottom of the table, minus 20.63. Go back, and I have 2 of them. So 2 times minus 20.63. I should be writing all the labels, and I'm getting a little lazy here. And then plus, and then it's 3 oxygens. So it's 3 times 0 because oxygen is an element and it has a heat of formation of 0. So now we just do all the math, put it all together. So if I were going to write this out quickly for you, I'll just do it really fast so that you can see it. It'd be a minus 571.66 here and a minus 593.66 there. So you're going to add those two together. And then from that, you're going to subtract the 2 times minus 20. So 20.63 times 2. You're going to subtract a 41, negative 41.26. Remember, when you subtract a negative, you're actually adding them. And your final answer for this particular problem should be negative 1124.06 kilojoules per mole. If you see that I've screwed up on anything, please let me know. All right, for letter C, carbon monoxide. Mon means 1, so we're going to have carbon monoxide plus oxygen yields carbon dioxide. And now we just need to balance it out. Change colors for a moment. Let's go with a green. And to balance it out, we're just going to throw 2's in front of both of those, and we should have everything. Oh, no, not quite. What did I screw up? Oh, no, I did it right. I did it right. Okay, so we've got the right number of oxygens. That's what I was concerned about. Okay, so now we're going to go ahead and do the same thing that we've been doing all along. We're going to keep looking them up in the table. So we're going to look up carbon dioxide on our table. So there's carbon monoxide and carbon dioxide. I have them already written down, so I'm just going to keep working with them. So I'm going to do the products first. So I'm going to do 2 times, and then carbon monoxide is a minus 393.509. And I'm done with my products. So now I'm going to subtract my reactants. Now I've got 2 carbon. Oops, I said that wrong, everybody. I said the words wrong. I'm sorry. The product was a carbon dioxide. So this was for carbon dioxide. And now I'm subtracting from it the carbon monoxide. I'm sorry to have said the wrong words there. And the carbon monoxide is 110.525, which means you're subtracting a negative. And so when we get it all worked out, we will have a minus 565.968 kilojoules per mole. All right, let me know if you have any questions about that one. Everybody say hi to my husband who came outside to have a little lunch. So where is he? There he is. Oh. My dog thought he was saying hello to somebody, and so she felt the need to bark. Okay, Trixie. Whoops, I didn't mean to do that. Okay, moving on to problem D. Okay, we have, I'm just going to balance this out for you quickly. Let's switch colors. I don't know what color to use today, so let's go with this one. So to balance this one out, we would use 3 for the carbon monoxide, and then we have the iron 3 oxide, and then 2 iron, and then carbon dioxide, and that should be properly balanced. So now we're going to subtract, remember, the products from the reactants. We'll look it up on the table, but I already have those numbers written down, so I'm not going to look up on the table for it right now. So the first thing I'm going to do, 2 times, and iron is an element, everybody, so it's a 0, plus, and then it's going to be 3 times, and carbon dioxide we've already written down. You're just going to have to pardon my noisy dog. So 3 times, and that was minus 393.509. And those are all our products. And now we're going to subtract our reactants. So we'll start with 3 times carbon monoxide, and we already looked up carbon monoxide once before. And carbon monoxide is a minus 110.525. And then we will add that to 1 Fe2O3. And the Fe2O3, we just have a 1 for the coefficient. It's going to be 824.2. And we are done. Now we just need to add it all together. Remember, when you're subtracting a negative, it's like adding it. So the final answer for this one should be minus 24.752 kilojoules per mole. If you see that I screwed anything up, please let me know. All right, let's try a new color. We'll do one last of these types of problems, and then we've got a few others that we're going to work through. Okay, this is letter E. I will balance it off for you. So 4 of the ammonia plus 5 of the oxygen yields 4 of the nitride oxide. No, nitrogen oxide. There we go, nitrogen oxide. And then plus the water is 6 water in that case. All right, I've looked up all the numbers on my table already. Remember, always we're going to do products minus reactants. So I'm going to start with my brackets. I'm going to do 4 times the NO, which is 90.25. It's actually a positive number. We don't see that very often. Plus, and then we're going to do 6 times the gaseous form of water, which has a very different number than the liquid form. So be careful that you're looking up the gaseous state of water. Okay, and those are my products. I'm going to subtract the reactants from that. So 4 times the ammonia would be minus 46.11 plus, and then 5 times the oxygen. Remember, oxygen is an element, so it is 0. So when we do the whole math, you should end up with a negative 905.468 kilojoules per mole. And in case nobody's been noticing, I definitely have not been paying any attention to sig figs, so don't worry about the sig figs right now. All right, I'm going to go ahead and switch to the next page. Now my daughter's out here. She's out visiting. Isabel, say hi. Hello. All right, let's see what we can do. So the next thing says draw a basic graph. I'm going to make this big so we can draw it well. So it says draw a basic XY graph and using actual values construct an energy profile for the reaction in 1B. Assume the activation energy for number 1B is 350 kilojoules. So if I draw my thing, we're going to have time on the bottom, and then energy is increasing. That's hard to write. I'm going to tilt the whole thing sideways. Uh-oh, what happened to my computer? There we go. Okay, that didn't work because my screen went the other way. I'm going to have to move that. There we go. Okay. Energy, E-N-E-R-G-Y. And then we're going to go ahead and put in the data that comes from that particular equation. So we had the starting molecules were 2H2S plus 3O2. That's our starting. Then we have to input lots of energy, the activation energy, in order to get it to actually occur, in order to get that reaction to happen. And then it falls down to a lower energy level. How did I know it was a lower energy level? Because when we calculated it, it was a negative number. So 2H2O plus 2SO2, those are the products from that particular reaction. So now the activation energy, be careful, the activation energy, let's try a new color here. I gotta get my head out of the way there. There we go. The activation energy is the energy that goes from the starting point to the top of the hill. So this is the activation energy. And in this case, we said it was 350 kilojoules. That's the activation energy. And then what we have been working out, what we've been figuring out all day today is this right here. This is the delta H of formation. And in this case, we calculated, I'm going to move my picture over there, we calculated that it was a negative 1,124.06 kilojoules per mole, and that means it is exothermic. All right, let's see, other things that I can put on the graph here. Oops. I could put the starting level, which was a negative 41.26. So I'd write negative 41.26. And over here, the answer was, I need a new color for that, sorry. So a new color would be that color there. And this one right here is a negative 1165.32. 2, and that would be kilojoules again. All right, so that's your general energy diagram, and this is the whole purpose of what we're doing in these problems right now. Okay, we're scooting back up. I wonder if I can make that window close. No, I can't. Okay, ethane thiol is a liquid with an obnoxious odor. It is added to natural gas fuels, so gas leaks can be detected by your nose. What is the standard heat of formation for ethane thiol? So this, either it's not on our table, or we just aren't supposed to figure it out. But they give us the final answer. So now we're just going to use a little bit of algebra to solve this one. So the first thing we're going to do is we're going to set it equal to, so minus 3754 kilojoules is what, now we do the whole rest of the equation. So in this case, oh, and have we balanced it? We have not balanced this equation. So let's get some balancing going here. So for the ethane thiol, it's a 2. For the oxygen, it's a 9. Don't you hate these big numbers? They drive me crazy. Carbon dioxide is a 4, sulfur dioxide is a 2, and the water is a 6. All right, now we're totally ready. Okay, so now what we're going to do is put in what we don't know. So we're going to start with the products, and we're going to get those entered in first. So 4 times, and then we're going to do carbon dioxide first. We've already looked that one up several times. 393.59 plus, and then it's going to be 2 times sulfur dioxide. We already looked that one up. Minus 296.83 plus 6 times, and it's liquid water in this case. 6 times liquid water would be minus 285.83. And now that's all the products. Now we're going to subtract the reactants. The first reactant we don't know. So we have 2 of the ethane thiol, and we're going to call its heat of formation X. And then we're going to add that to 9 of oxygen, which is 0. Isn't that convenient? So now we just solve for X. I'm not going to go through all the algebra for solving for the X, but in this case, if you go through all the algebra, you will find that X equals and minus 64.485. And that would be the delta H of formation for ethane thiol. Ethane thiol. There we go. All right. Next one is exactly the same type of problem. I wonder if I can make that go away. There we go. Okay, this is the exact same type of problem here. So they give us the answer. So I'm gonna go ahead and change colors right now. They give us the answer, minus 3677 kilojoules. And now we're going to take the products, and what we're looking for is P4S3. That's what we don't know. That's going to be our X today. So, and I better balance the equation. And again, it's got some ugly numbers. So an 8 in front of the oxygen, the P4O10 stays the same, and then a 3 in front of the sulfur dioxide. And so we set it to minus 3677 kilojoules. And we do the products first. So this part we're doing first. So the P4O10 is I've already looked it up, minus 2984 kilojoules per mole, blah, blah, blah. Plus, and then we're going to do 3 times the sulfur dioxide. We've done that one so many times already now. 296.83. We should just have that one memorized, right? Okay, that's our products minus our reactants. Well, we've got 1 in front of the P4S3, so that's going to be our X. And then we add to that 8. Oh, look at that. Oxygen is an element. So we're just solving for X. Now when we solve the whole thing for X, we should get X equals, I'm not going to go through all the algebra here, but minus 197.49. And that is the delta heat of formation for P4S3. All right, moving on. Now let's see if we can tie this into biology a little bit. The following reaction is the breaking down of the carbohydrate glucose. We all should be familiar with glucose. How much energy is generated by breaking down 1 gram of glucose? Hint, this is just a simple stoich problem. Minus 2,803 kilojoules is for 1 mole of glucose. What would it be for 1 grams. So there's a few things that we need to make sure we do. First of all, we need to make sure that the equation is balanced in case that has any kind of an impact on our results. And I think that this time it actually doesn't have an impact, but in the next reaction it will have an impact. So now what we're looking for, this is just stoichiometry, you guys, from a couple units ago. 1 gram of C6H12O6 times, we want to convert it into moles, so 1 mole, and the mass, I'm just going to add it up for you, 180 point, can't read my own writing, 156 grams of C6H12O6 times, do another conversion factor. We want this in kilojoules, so we need to get rid of the moles. So we're in, do you see that we're in moles right now? We've crossed off grams. Now we're in moles. So this was kilojoules for 1 mole. So 1 mole can go on the bottom, and this number goes on the top. Minus 2803 goes on the top. And so you multiply them all across. So 1 gram times 1 mole times negative 2803. Whoops, I should have written kilojoules, divided by the mass of the glucose. And for an answer, you get a negative 15.56, and our unit would be kilojoules for 1 gram of glucose. Now let's turn the page and let's look at the next question, which relates. I think it's a super interesting question. The following reaction is the body breaking down the fat glycerol trimyristate. I don't know that one. So anyway, we've got this enormous molecule, and we need to balance this equation, and I'm just going to write it out for you because nobody wants to balance this equation. So I will do that for you. 2 of these, that is going to be important, the fact that we have to put a 2 in front of it. 127O2, 127, oh my gosh, it's like the biggest molecule we've ever seen. 90 CO2s and 86 H2Os. All right, and then we see that the delta heat of formation is minus 55,640. So it says how much energy is generated by breaking down 1 gram of this particular fat. So same exact way to set it up. We're going to start, it's just a stoichiometry problem. So 1 gram of C45H86O6 times, and then we're going to put 1 mole, we're converting it, 1 mole, and then its mass is 723.177 grams. 45H86, oh my gosh, this takes too long to write, right? All right, and then we want to convert it because we said that this was the amount of energy it takes in 1 mole. So we're going to put 1 mole on the bottom. And oh, sorry, that's 2 moles. That's for every 2 moles because there's a 2 right here. So that's why it's 2 moles. So I got to put a 2 on the bottom. And then it is the number 55,640 kilojoules. When we work out all the math, our answer ends up being a negative 38.47 kilojoules. Okay, so that's our answer. So now the last question, we're almost done. Compare your answers from 6 and 7. In terms of energy, explain why the body stores fuel as fat. Well, fat stores way more energy than carbs do. Sugars. All right, and then letter B, data commonly given by nutritionists says that your ratio for fat to carbohydrate should be 9:4. Does your data from 5 and 6 match that? Well, let's take a look. You had a minus 38.47 kilojoules for your carbohydrate, for your glucose, and we had I'm sorry, that was for the fat. And then a minus 15.56 kilojoules for the glucose. So that equals a 2.47. If we did the 9/4, it would come out to 2.25. So we're comparing these two, and they're pretty similar ratios. So we would say yes, the answer, they are similar